Hey guys, welcome to Fraser's GAMSAT. My name's Christian and I'm one of the Section 3 tutors here. And so what we're going to be doing today is looking at a number of different STEMs across the sciences. So hopefully if you have a look on the website, you've gone through the questions yourself, attempted those, and let's take a look at how we would answer all those questions now. So jumping down to the first one, what we have is we're trying to work out what diagnosis we would give a person given these specific values. So as we're reading, what I'm going to do is just identify those on the actual graph and try to work out if I can see the answer. So having a look at, first of all, we have a PCO2 level of 20 milligram mercury, PCO2 being over here, 20 milligram mercury down here. We have an arterial blood H plus concentration of 45. Jumping up, what we have is, where are we? Over here, and looking at 45, we're on this axis over here. So just quickly joining those up, I guess coming down along here, and then working out that 45, we're at this point. Just to confirm, I saw that there was a third measurement, and what this was the arterial plasma of HCO3 minus, and that is of 10 millimole per litre. And so just making sure that's the case, we are roughly at 10 millimole per litre. So what are we being diagnosed as? We can see that we are within the region of metabolic acidosis. So without needing to look at the other responses, because they're not actually part of where we are with these measurements, metabolic acidosis should be the answer. Cool, so the next question, what we're doing is trying to work out the minimum number of measurements that we can use to try to diagnose someone like we did in question 1. So jumping up over here, basically keeping in mind that each of these regions over here would be representative of something that is, diagnosis, same with up the top. The one that really stands out to me of being an issue is this partial pressure of CO2. Because for example, if we were to focus on 20 milligram mercury again, what we see is that this number, what it does is go down here, and it really does actually cut through everything in that regard. So it can prove a little bit problematic because it does continue through a number of diseases. So instead, what we're going to try to do is pinpoint something else. So having a look at these over here, what we see is that any one of these are really handy because they can specifically pinpoint a certain spot. And so really what we have is a minimum of 2 measurements. If we had 2 measurements, what we can actually do is find precisely what we're trying to diagnose. So the answer for 2 would be B there. Okay. Now for the third one here, it is a little bit different because of the fact that we can't just go straight to the graph, work out one specific answer and knock off all the rest of them. What we actually have to do is methodically go through each of the different options and pinpoint whether the logic actually makes sense across the board. So let's go through A through to D and see if the logic actually makes sense. What we have in the first one here is that we have somebody with a PCO2 level of 40 milligram mercury. What they're saying is they cannot be diagnosed with respiratory acidosis or respiratory alkalosis. Now jumping over to the graph, finding that 40 milligram mercury and tracing that line here, we do see that the only thing that this line sort of intersects is the normal and none of those diseases that were listed. So fresh off the bat, I'm inclined to say that this one does seem that it actually is right. But let's go through the rest of them, and provided all those actually, the logic doesn't make sense with those, we can in fact go with A. So with B, what we have is chronic respiratory alkalosis has a higher pH cutoff than acute respiratory alkalosis. So chronic respiratory alkalosis, they're saying that it has a higher pH than acute respiratory alkalosis. Now having a look at the pH values over here, this does not actually make sense. Chronic respiratory alkalosis actually has a lower pH, keeping in mind that the pH is increasing in this direction and not the other way around. So it doesn't seem that B actually makes sense. Looking at C, what we have is a patient reading could have an arterial plasma HCO3 minus of 40 mole, PCO2 level of 90, and arterial of pH of 7.25. So having a look, HCO3 of 40, so marking that over here. What we have is a PCO2 level of 90, marking that over here. And finally, that the pH was 7.25, and 7.25 being over here. So what I'm going to do is trace where these lines actually intersect. And what we find is that the pH with these measurements does not correspond to 7.25, it's actually closer to 7.3. And so as a result, with that in mind, it doesn't actually make sense that C is right either. Cool, so a patient in D that has developed acute respiratory acidosis will over time transit into chronic respiratory alkalosis. Now, without looking at the graph here, keeping in mind our reading of the stem, this doesn't make sense because we didn't actually gain any information about progression of disease. And so, although this actually might be true, it's not actually presented within the stem itself. So the logic here does not actually point to D being correct either. So because A was the one that we flagged, we'll be going with A in this case. Okay. Having a look at number 4, what we have is the pH of 1 times 10 to the power of -1 mole per liter of HCl. This pH is 1. And the pH of H2CO3 at this concentration is what? Now, straight away when I read this, I'm inclined to go into the maths over here as described within the stem. However, before we jump into any maths, there is a great deal of virtue in just stepping back, looking at the options that we actually have present, and seeing if anything makes logical sense. So the first thing that I'm going to try to test is, well, I guess recognizing that HCl is a strong acid. Now, what they're saying is that this HCl has a pH of 1. The H2CO3 is a weaker acid. Now what this means is that the H2CO3 will have a pH somewhere between 1 and 7. And the reason why I say that is because being a weaker acid, it will not have a pH as low as the HCl, but the pH won't be higher than 7 because otherwise it would be considered a base. So because of that, I'm going to check the options and see if there is a pH that's between 1 and 7. And looking at the options, there is indeed only one that is the case, and so C would be the answer. So without actually going into the maths itself and looking at the formulas, we're able to deduce the answer here very, very easily, very, very fast. What we're going to do is something very similar for question number 5. And the reason why I say that is because upon looking at all the species within the options in question 5, we see that something really does stand out as being quite intuitive. The first thing is that HCl is the strongest acid out of them all, and that is something that we all know. Secondly, what we see is that there are 3 species. Let's have a look at the bottom, where over here, these two are related. The one on the right is actually a protonated version of the one on the left. Now, looking at those 2 species, when we're trying to ask which one do we think would actually be a stronger acid, of course, we're going to tend down the path of the one with the lower charge will be the one that has a greater, I guess, ability to offload their protons. The reason for that is because the one on the left has a charge of -2. So the ability of that species, or I guess tendency for that species to give up a proton in that scenario would be diminished because of the fact that there is an opposite charge. So why would it want to give out another proton? And so as a result, I'll be inclined to say that the H2PO4 single minus is a stronger acid than this one on the left. By that same logic, we actually see that the H2CO3 does not have a charge. And as a result, I'm going to infer that this species over here actually is a stronger acid than this one because of the fact that without that negative charge, it has a greater tendency to offload that protein. And so as a result, what we actually have is A. We have the highest acid being the HCl, the next one being the species without a charge, the next one being the species with only one negative, as we can see there, and the final one being the weakest acid, the one with the highest negative charge, the one that has the least tendency to give up a proton, and that being last. So A would be the answer here. Great.